On our first normal distribution question from S1 at Excel, we've got a scenario here of a normal distribution which has mean of 155 and standard deviation of 3.5 minutes. Okay, the way we write that's always worth writing is that M is normally distributed with mean 155. And what else do we, how do we write the other bit? And the standard deviation, what do we write here? Yeah, it's 3.5 squared. We do tend to write it like that because it's the mean and variance then that we have defined in as our normal distribution. Right, so the first question, 3 marks, and I presume it's probably meant to be relatively straightforward. Good diagrams are always a good idea, okay? And if you put on your diagram where the distribution actually is, where it is, you will see the kind of probability. It's always useful to see whether it's more than or less than a half. Because in fact, normal distribution questions, these standard ones, you're either reading a number or you're taking away 1 from the number. So it's always worth doing a diagram. Some people don't like doing diagrams, but it's always a good idea. So basically, x is 160, but our mean is 155 there. We've got 160. So we're being asked for that area effectively. Okay, so because the whole area under the normal distribution curve is 1, yeah, this particular, and so it's half if you go above 155, we're looking for a number less than 0.5, so that's always useful to know. What do we actually do though with a normal distribution when we have a mean and variance? What do mean and variance given? We want to, what kind of do we do in order to? Yeah, and what that equation? What do you mean by that? Z. You kind of change it to the Z distribution, don't you? Z is equal to x minus mu divided by standard deviation, little sigma. Okay, so we change it to that. In this case, obviously x is m. Okay, so we change it to that, which then, because our Z distribution is basically normal with mean of what? The Z is normal. What's the mean of the? No, the standard one, the standard normal distribution. It's got a mean of 1 and it's got a mean of 0 and a variance or standard deviation of 1. Okay, so that's what you're doing when you're changing things to those tables that you can read. You're changing it to this distribution here. So just to answer the question, the probability that m is greater than 160 is the same as the probability that this z thing is greater than 160 minus 155 divided by the variance, which is 3.5. Okay, so we've got that as our normal distribution calculation. Okay, now that equals 160 minus 155, some number slightly above 1, I think. Z is greater than, can you say that again? 1.428. Right, okay, so 1.428, and again, if we're to look on the standard normal distribution, Here, that's a distribution with mean 0. It's 1.428 we're reading, okay? But if we go to our table, our table here, and we read 1.428, where is it? It's a little bit below here. We read 1.428 or 1.43 being the closest one. Okay, what number does this give us here? The number 1.43, that number there. What does that number represent? The no Yeah, which area? Yeah, so in fact, this number here would be the 0.9, whatever it was, and so we need to take that number away from 1. So it's 1 because we want the number greater than, so it's 0.9236. Okay, and if you work that out, that equals 0.0764. Okay, so that's the first part of the question. The second part of the question is got a wider range, but before I ask that, does it matter in this case whether it's a this or a this, you know, in terms of that or that? Could I have written that or that and got the same answer? Would it make any difference with the normal distribution? Does it make any difference whether I have what's called a strict inequality or an inequality? Because it's funny, because they've changed it here from what is a strict inequality to just an inequality. Strict meaning it can't be equal to that, and they've switched from one to the other. And in the first one, I think they've done it deliberately. They didn't put it in. So anyone want to commit themselves? You have. You don't think it matters, Alice? What do you think? No, it doesn't. Any ideas why not? Yeah, it doesn't make any difference, because I think we had this. I think you had this discussion with Dan. Was when the probability of one particular number is 0. Doesn't, I mean, let's not. Do you remember that? The probability of getting exactly 160. Let's not go into a big in-depth discussion about that. But the probability of it being exactly 160, because you talk about a continuous distribution, is 0. But I don't want to have a philosophical conversation about that. It doesn't matter. Okay? It doesn't matter whether it's strict for the normal distribution. If you're dealing with discrete random variables, though, because that's discrete, you've only got a certain number of values, then it's a big deal. Whether it's if it's a discrete distribution, it's a big deal whether it's equal to or allowed to be equal to or not. Okay, so we happy with that? Yeah. Okay, so let's just go on to the next bit. This bit off. Okay, so for the part B, let's do a diagram for it, because always it's the first thing you think of, isn't it? I want to do a diagram. So this time it's going between 150, which is slightly less than the mean, to 157, which is slightly more than the mean. Unhelpfully, it's not equally spaced though. If it were, because this one's 5 away from the mean, whereas this one's only 2 away from the mean. So we call that 157, just slightly above halfway, and 150. So we've got to work that area out. effectively. Okay. Well, like we did before, we will change it to the Z. So we will have the probability that our value of M lies between 150 and 157 is exactly the same as the probability that Z lies between 150 minus 155 over 3.5 is less than or equal to 157 minus 155 over 3.5. Okay, so that equals, I've done that calculation. What do those equal to? Minus 1.428 and 0.571. Okay. Right, so, right, let's get rid of this bit. Okay, so, any ideas? Any ideas here? Yeah, so what you could do is just say, you could just say it's 1 minus the probability that, and let's make sure our inequalities go the right way around, but the probability that Z is less than or equal to minus 1.428 minus the probability that Z is greater than or equal to 0.571. From the diagram, we've seen that. Can you see it? Yeah, it's the whole area is 1, so the green bits were just taken away. So that's that's the green bit to the left, that is, and that's the green bit to the right. Okay, so you can then treat these separately. I mean, what you can do a little bit is kind of cheat, because obviously you're not allowed to look at the negative numbers anyway. You're not allowed to, there are no negatives in the table anyway. We know that this number here has got to be less than 0.5. You know, so what we can do is just say, right, let's read the 1.43 again. So that's 1. So if I go to read 1.43 in the table, it's 0.9236. Okay, like it was before, same as before. Why did we have it before? But because we know the area is, because we know that area's got to be less than a half, we know we've got to take it away from 1. So it's almost like not fiddling around with it, not thinking too much about it. Is it more than half or is it less than half? If it's less than half, it's got to be one or the other. And because we know it's got to be less than half, we know that for that bit we need to take it away from 1. Okay, there's a lot of jiggery-pokery we could do because obviously it was negative, and there's lots of things we could do. But in fact, whether it's a negative value we're looking at here or a positive value, in essence, it's going to boil down to either taking away from the number from 1 or not. And if you've got a good diagram, you can see that. Okay, and this one here also read what it's going to be 1 minus. So read that 1 minus, and that, let's look for the 0.571. Again, you don't have to what's called interpolate, thankfully. You can just go for the nearest one. Okay, you don't have to kind of say, well, it's going to be in between 0.7157 and 0.719 and adjust in proportion or anything like that. Go for the closest one. It's easier and quicker and it's accepted. So 0.7157. And that'll be our answer. Okay, if you could work that out for me, that would be good. Yeah, 0.6393. Seems reasonable somehow, doesn't it? Because it's gonna, we've got a the standard deviation is 3.5, and we're more than one this 150 is more than one standard deviation from the mean to the left. Okay, so it does seem like a reasonable answer. Okay, I'm sure it's correct. Okay, so that's question B. Okay, and question C, this is going to be one of these backward questions which are more confusing, because here we're looking for a value and we're given a probability, 0.3. Okay, right, I will, maybe what I'll do is go here. Okay, so if we're looking at part C, again, first inclination is to draw a diagram, get a picture of the kind of number we're looking for. So for part C, okay, for part C, it's saying find the value of m such that if it's less than, the probability of being less than is 0.3. Okay, so that number there is 0.3. Okay, right, let's say this is the M distribution, the values of m's, and this is our z. In terms of its position, it's in exactly the same place, it's just the number here will be different. Okay, so the number in the middle for our m, the mean, is 155. Okay, the value in the middle here is, for the z, is, I've already mentioned it, 0. Okay, so we want to find, this is the number we're looking for here, 155. Okay, now, this number here, we know is going to be negative. Okay, right, now, we almost want to, when we're looking at the z thing, we almost want to find what the exact opposite is, if you like, what the positive number is here. Do you get what I mean? Because that's 0.3. So we always have to look on the positive side if we're looking at the tables. So this area here is 0.7. So that's the number we need to look for. But this number here is obviously going to be positive. This number is going to be negative. So what we need to do is go to the tables, look for 0.7, the closest, and remember we're working backwards. We've got an area, we've got a probability, and we want to find what the z number is. Yeah? So go to the one that's closest. You do not need to interpolate or anything, even though it looks like it's halfway between these two. Yeah? You could say it's 0.525 or something like that. You don't have to. Go to you can just go to the closest one, 0.52. right? But it's not 0.5, it's 0.52 there, but this number which we're actually looking for is what? Not 0.52 minus 0.52, because any number to the left of the mean of the Z distribution is minus, so it's minus 0.52. So I've done all that, and haven't actually written any equations yet. I've just fiddled around with the diagram. A graphical approach is a good thing. Okay, so we've got the probability that m is less than m equals to 0.3 is the same as the probability that this z that z is less than or equal to m minus the mean, which is 155, divided by the standard deviation, which is 3.5. That's equal to 0.3. But we've already read this value. Because we now know this diagram here tells us that the probability that z is less than or equal to 0.3, that's what this is equal to minus, oh, wrong way around. That diagram is telling us that. That's what we fiddled around to find. That diagram is, this diagram here is telling us that the probability that z is less than or equal to minus 0.52 is 0.3, which is what we're looking for. So we have, after all that fiddling around, m minus 155 over 3.5 equals to 0.3. And we can solve that quite easily. We have m minus 155 is equal to 0.3 times 3.5. Add that on to 155. And what do you get? Oh, that's right. Deliberate error. That here is equal to minus 0.52. This is minus 0.52, so that's minus 0.52. Thank you. So that equals to m minus 155 equals to minus 3.5 times 0.52. And that gives me m equals to 155 minus 3.5 times 0.2, which is equal to 153.2. Okay. Incidentally, had I kind of not persisted with that craziness of putting the number 0.3, which is a common error, by the way, I would have, and you should have done too, would have reflected back and thought, that's got to be wrong, because I would have had an answer more than 155, and I'm expecting an answer less than 155 in order for the probability of it to be 0.3. So honestly, thank you for pointing it out, but I would have noticed. Okay.